The topic of today's video is conservation of matter. And I'm going to start off by making sure that we're all sort of familiar with how you write chemical reactions, because we will be looking at examples of chemical reactions today. And so when you write a reaction, let's write how to write reactions. It's actually pretty simple. It has three main parts. On the left side, you write what you're starting with. So I'm going to write here starting materials. And then you show that you're going from your starting materials to your ending materials. So what you start with, and you go to what you end with. And in chemistry, we call these reactants. So they are the things that are reacting. And over here, we call the ending materials, or what we end up with, are products. So you do need to know both of these terms. And then this right here is our reaction arrow. So again, this is just a way of writing what we start with. You draw an arrow to show that we started with this and we're going to this, our products. Let's take a second and define conservation of matter or of mass. I'm going to write it of mass here so that you get familiar with seeing it in both ways. So conservation of mass is a sort of deceptively simple idea, which is that nothing can ever just disappear. Nothing can ever just disappear, only rearrange itself. And you know how I love to take really, really simple ideas and then turn that into powerful tools for problem solving? This is no different. This is the same thing. We're going to take this super simple idea that nothing can just disappear. It can only rearrange itself to solve seemingly complex problems. So let's start off by doing a quick example. So I'm going to show you how we're going to take sort of a complex looking thing and turn it into something that's very easy to see and understand. So let's say that I write a reaction, and I'm going to write our reaction using our nuclear notation that we have been looking at. And so I'm starting off by writing a hydrogen atom. This is the element symbol for hydrogen. And I've written an atomic number of 1 and a mass number of 1. We're going to get more into that in a second. And then I'm going to react that with, so I'm going to add something else so that I'm still on my left side because I haven't drawn my reaction arrow yet. So I'm going to react that with another hydrogen, but this one's going to have an atomic number of 1, of course, because if it's hydrogen, it must have an atomic number of 1. And it's going to have a mass number of 3. I've drawn my arrow now, so now I'm telling you that these two things are what I'm starting with. And now what I end up with is this. I'm going to write that I end up with a helium atom. And now if it's helium, it must have an atomic number of 2. If you don't believe me, look at your periodic table. Helium has an atomic number of 2. And I'm going to draw that it has a mass number of 4. Okay, so what I want to do is show you that we can sort of understand this using this really, really simple idea that nothing can ever just disappear, only rearrange itself. Because you can memorize this reaction, but there are so many different ways for things to react and so many different types of reactions that in the end, that's not really to your benefit to attempt to memorize things like that. So instead, let's try to understand it. So I'm going to draw this time let's see, I'm going to draw my protons in red. So let's draw this atom right here. And I probably should have spaced it out some. You know what, maybe I will space it out some just for the sake of us not getting squashed. There's plenty of space here. So let's do that and space this out just a little bit. And space this out a little bit as well. And our final atom is going to go over here. Okay, well now this gives us plenty of room. So I'm going to draw this atom right here. And so the first thing I want to do is draw my proton, because I know that it has to have a proton. So I'm going to draw it like that. And I'm going to put a little plus sign in the center so that I remember that this is a proton. And since we're going to be drawing a lot of these, I'm actually going to copy this and paste it and just have it ready for me to use here, because I'm sure we're going to need it very soon. So here's my proton for my hydrogen, and my mass number is 1. So what that actually means is that I don't have any neutrons, because remember that our mass number is the number of protons plus the number of neutrons. Well, if it's 1, then I already have that here, right? I can't add anything else because that would give me a larger mass number. So I just need to leave it how it is. So let me now draw our electrons, and I'm going to draw our electrons on a ring, and hopefully you can forgive my, oh, it actually wasn't too bad. Here we go. This is an okay ring, and I'm going to do the same thing, copy and paste this, because I'm sure we're going to need more rings as we go. And so I do not have a charge on this atom, right? If I had a charge, that would be written right up here. Like if I had a charge of +1, for example, it would have a little +1 here. But I don't have that. And so what that means is that my entire atom, counting up all my positive and negative charges, I need to have the same number of positive charges, or protons, as I do negative charges, or electrons. So in order to make this a neutral atom, which it is, I need to draw an electron in. So let me do that now. I'm going to draw my electrons this color. And of course, my electrons are actually really, really teeny. Let me make it maybe a little smaller than that. Okay, so my electrons are supposed to be very, very, very tiny. But for the sake of us being able to actually see my drawing, I'm going to make it visible to us. And let me just draw a little negative sign in there. Maybe I'll draw it with a tinier pen size to see if I can make that clear. I guess I'm just going to have to do this. Okay, hopefully you can see that that's supposed to be my electron. I need to just let it go. It's beautiful. No, hold on. Okay, that's going to be good enough. So let me copy and paste our electron as well, actually, because we are going to want that as well. Hold on a second. Come here, little electron. Let me copy and paste you, my little electron. We put him up here, and we are ready to use him again when we need to. Okay. So I've got this atom figured out. Now let me see if I can quickly make my other atom here. So this is another hydrogen. And so I know for a fact that I'm going to have to put a proton, right? Just one proton, because it has a mass number of 1. We know that. But here, I'm sorry, it has an atomic number of 1. But here it has a mass number of 3, which means that I am actually missing something here. I need to draw in my neutrons. So let me draw in 1 neutron here. Let me try to make it about the same size as my proton, because it is. And for the sake of things looking as beautiful as possible, I'm going to copy and paste that to make my second one, if I can. Here's my second neutron. Okay, so that makes sense, because we should have a mass number of 3, which means we want to have 1 proton to make sure that it's still a hydrogen atom, and then we add neutrons until we get to our mass number of 3. And now let's work on our electrons. So here's my ring for my electrons, and it's a neutral atom again, right? It doesn't have a charge up here, so I need to add the same number of electrons as I have protons, meaning I have to have the same number of negative charges as I do positive charges. Well, even though this atom looks different than the last one, it actually still only should have 1 electron. So let's do that now. Let's add our electron to it, just somewhere on that ring. All right. And now let's come over here and make our final atom. I'm actually just going to start off by copying and pasting this, because there are going to be a lot of similar components, and then let's see what we need to adjust. So this is supposed to be a helium atom. That means I need to have 2 protons. So let me make another proton right now and put that in here. Okay. And then our mass number is 4. So let's just see, we have 1, 2, 3, 4 particles in the nucleus. We have 2 protons and 2 neutrons. Well, that's good. We're all set. And then now, once again, we have another neutral atom, meaning it has no charge. So is this a neutral atom the way I've drawn it? In order to be neutral, it would have to have the same number of positive charges as it does negative charges, which means it should have the same number of protons as electrons. So right now, it is not neutral the way that I've drawn it because it has 2 protons or 2 positive charges, but only 1 electron. So let me just stick another electron on there. And then now we are ready. We are set. That's what we needed in order to complete this drawing. So to show you that this is a good example of our conservation of mass idea, let's break down what we've drawn here and just count up our particles and make sure we understand where everything is. So our particles here should be, let's draw it like this. Let's write down the number of protons that we have. Let's write down the number of neutrons that we have and the number of electrons that we have. And get used to seeing this notation. A little p with a plus sign just represents protons. An n with a 0 sign represents neutrons, which have 0 charge. And our e with a negative sign represents electrons, which have a positive charge. So let's do the same thing with all of these here. So here's going to be our protons, our neutrons, and electrons. And protons, neutrons, and electrons. Okay. So over here, let's just count these up. So I have how many protons? Just the 1. How many neutrons? 0. And how many electrons? 1. Okay, I just draw a line through the 0 so that nobody thinks it's an O, which could happen at some point. So I'm going to draw a line through it sometimes. And then over here, we have 1 proton, 2 electrons, and 2 neutrons and 1 electron. And then over here, I have 2 protons, 2 neutrons, 2 electrons. So what I'd like to prove to you now is that from our starting materials to our ending materials, we did not actually change the number of particles that we have. So let's take a look at and prove that to ourselves. So if I sort of draw in our plus sign and our reaction arrow, I started on this side with 1 proton in this atom and 1 proton in the other atom. Well, in total, I should have 2 protons, right? And if our conservation of mass is correct, then I shouldn't lose any of these. None of them will disappear. So let's actually come over here and see that sure enough, we have 2 protons. They've just rearranged into 1 atom instead of 2 separate atoms. If we look at our neutrons, we have 0 in this atom, 2 in this one. And so sure enough, when we look at our product, we still have 2 neutrons. And then again, with our electrons, we started with 1 in this atom. We had another 1 electron in this atom. And so if we counted them up on this side, 1, 2, they should equal the same number on the other side, 1, 2. And they do. So this is a perfect example of our conservation of matter idea. So I'm going to now do, let's do another example, okay? So I'm going to erase this stuff, and we're going to look at another example. So let's look at our example 2. So this time I'm just going to draw some atoms for you rather than writing them out to start, because I find that it's easier to count up our particles like that. And then we're going to work on other ones where we're not having to draw out the whole thing. So to start, I'm going to make some atoms here. So I'm going to make an atom that has, let's see, I'm going to give me just a minute to build these for us here. So I'm going to start with, let's maybe draw our actual atoms first. So we're going to have 1 here, and we're going to add another 1 here. And then we're going to have our reaction arrow. And then we're going to have another atom as our product. Okay. And in our first atom, we're going to have an atom that has just one proton and one neutron. And this is going to be a neutral atom, so I do need to add an electron here as well. Because if it's neutral, it has to have the same number of protons as it does electrons. In my next atom, I'm actually going to copy this because my next atom will have also just one proton, but it's going to have an additional neutron. So let me put that other neutron in here. So there's my other neutron. And again, this needs to be on a neutral atom. And so let me copy and paste to make sure that I have my electron here as well. Just add an electron there. So see how each of these has one electron and one proton, so they're both neutral. And then what I want to ask you is, oh, I'm missing one more thing in my product here. So my product is actually going to have a neutron as well. So it's not just going to have an atom, it's also going to have this sort of random looking neutron hanging out there. But that happens sometimes. So this is a real example. So let me add my plus signs in here so that we see that our starting materials are these and our ending materials are these, or our reactants are here and our products are here. And so if I sort of set up the same thing that I set up last time to count out the number of particles, let me just do that now. So I'm going to count up my number of protons, my number of neutrons, and my number of electrons, right? And I don't want to do that just for one of them. I want to do that for all of them because I know that none of my particles are going to disappear, right? They're going to rearrange, but they're not going to disappear. So let me draw these in here. And let's just start filling out what we know. Maybe I'll make it clear that this is what we're not sure about yet, right? And so here we have one proton, one neutron, and one electron. Here we have one proton, two neutrons, and one electron. We don't know these yet. And here we have 0 protons, we have 1 neutron, and 0 electrons. It's just a neutron. It doesn't have anything else. So if we start with our protons here and see if we can figure out, and you know what, I just want to show you all, we can also write this as like an equal sign just to show that the actual number of particles will be the same, right? So let's see, on this side we have 1 plus 1 proton. So that's 2. That means on this other side we must have 2 protons. Well, our neutron doesn't contribute anything to that. And so this has to be the number 2. Now let's look at our neutrons. So again, on this side we have 1 plus 2 neutrons, so 3 in total. Well, we must have 3 neutrons on this side as well. So we have this 1 neutron that contributes here, and so this one must be a 2. Let's just make sure everyone's clear on that. So on the reactant side, I have 1 plus 2, I have 3 neutrons total. And on the product side, I have 2 plus 1, 3 neutrons total. So this makes sense. This is correct. And then now let's look at our electrons. On our reactant side, we have 1 plus 1 electron, 2. And so on our product side, we must also have 2 electrons. And there's no electron around this neutron. That's how it's been drawn here. And so I must have 2 electrons in this sort of mystery atom that we have here. And so now let's draw it in. So if I asked you to draw your resultant atom, which sometimes I may ask you to do, we can do that. So let me start with, I know I'm going to have to add stuff to this, but let me just start with this nucleus to save ourselves some drawing time. But we definitely are not done because I'm supposed to have 2 protons here. I've only got the 1. So let me start by adding another proton here. And then we've got 2 neutrons. That's what it needs. So we're all set with our neutrons. And I need 2 electrons. So let me add those 2 electrons in now. So here I'll have 1 electron and another electron. And so now I have completed this reaction. I've completed this reaction. Okay, let's do another one like this. This time I'm actually going to use some of this stuff again. So let's do this. Let me just write our example 3. Example 3. And so I'm going to actually use this one here. I might as well just copy the whole thing because we know we're going to have to calculate all parts of this. And so let's just save ourselves some work. So here I'm going to start off with a hydrogen atom that has 2 neutrons. So it'll have a mass number of 3 because it has 3 particles in the center. And my product is going to be this whole section over here. This is going to be my product side. And so I want to know, how can I complete this reaction? Now you might be thinking that's very easy because it's going to look very similar to our last one. And you're exactly right. It is very easy and it is going to look very similar to our last one. I am using this as an opportunity to show you that we can predict things that are in the reactant side as well. We don't have to only predict what we'll get on the product side. We could do the same prediction for our reactant side. So let's just do it. Let's see what we get. So we want to know how many protons will this atom have, how many neutrons will it have, and how many electrons, right? So here, this time, the side that's complete for us is the product side. So I'm actually going to start counting on this side and see what I need to fill in to make it the same on the reactant side. So I have 2 protons and 0 protons on our product side. So I know that my total number of protons that I should have on my reactant side should be 2. Well, I've already got 1 in this atom. And so in order to get to 2 on this side, I need to add 1 over here. So look, let me just sort of show again that we can almost imagine this as an equal sign, and our protons should equal the same number of protons on each side, even if they're rearranged. And then over here, I have a total of 1, 2, 3 neutrons, right? I have 3 neutrons in this side. And so I need to have 3 total on the reactant side as well. I've already got 2 here, so I'm missing 1. And then I also know that I have 2 total electrons on this side, on the product side, and on our reactant side right now I only have the 1. So I'm missing 1 electron. And rather than draw this all out, I'm going to recognize, hey, I have that same atom right here. So let me just copy and paste that to complete this example. Okay, so I ended up with the same reaction. I've just switched the order that I've written it, but it's actually the same exact reaction. However, in example 2, we had to predict one of the products, and in example 3, we had to predict what one of the reactants were. And now let's move on from drawing these out, because while it is a very useful tool to use, and I do recommend that you use it as a tool frequently in exams and when you're trying to solve problems, we also want to be able to do it without having to draw it all out. So let me give you another example. Let's do this. Example 4. And now, rather than draw my atoms, I'm going to write it in our nuclear notation, how we sort of previewed the very first example that we did. So in this one, I'm going to start with a hydrogen again, and this is just a hydrogen with a single proton in the nucleus and no neutrons. And I'm going to add to that some element. I don't know what the element is. I don't know what the mass number and atomic number are. That's what we're going to find out. So you might see problems written this way. You might also see them written this way. Just you could see maybe a question mark. But I do want you to just be comfortable with seeing this representation of like, this is what you need to find. And then my product side, I'm going to have a helium atom. I know my atomic number must be 2, and I'm telling you that this is a helium-4 atom, so it has a mass number of 4. Okay. Let me give you all one shortcut to take. There are no charges on here, and I'm not even really concerned. Like, I don't need to know the number of electrons to find the answer to this problem, because since nothing is charged, when we're talking about reactions such as these, where we have like starting products that are different from our ending products, I'm just not even going to worry about my electrons right now. Not right now, because if there's no charge on this side, then overall it must be neutral on this side as well. And this atom is neutral, and so this atom is going to have to be neutral. So if you're not totally following that right now, that's okay. I just want to put the idea in your head that right now I'm not even going to worry about my electrons, because I have no charges anywhere. I have no charges anywhere, so they're not going to really be very important to figure out for me right now. So instead of writing all 3 particles, I'm actually just going to focus in on my protons and neutrons, because that is what's being rearranged here. So I need to find out my protons and neutrons. So let's start with our protons, because that is by far the easiest thing to fill in here. It's just our atomic number. It's just our atomic number. So for those of you who might need a reminder, this bottom number right here is our atomic number. And it tells us the number of protons. All right, so you need to know that by now. If you are finding that you're not being able to remember that, then maybe make a flashcard for yourself or remind yourself in some way. So on this atom, I just have 1 proton. I don't know this one yet. And on this atom, I have 2 protons. So we don't even need to move any further yet to be able to fill in the number of protons of this atom, which would actually give us that atom's identity as well. So remember that we can imagine this is our equal sign. So if I have 2 protons on this side, I must have 2 protons on the other side of the equation as well. And so I have 1 from here. I know that I need to have 1 proton here. Already I know, oh, it's a hydrogen atom, right? It must be a hydrogen atom because it has 1 proton. And now let's look at our number of neutrons. This is a little bit trickier. Remember that our mass number is our number of protons plus neutrons. So let me write that. Excuse me. This is our mass number, and it tells us our number of protons plus neutrons. Oh, let me write number, plus our number of neutrons, right? Well, in this example, this first atom here, we have a mass number of 1. So our protons plus neutrons is just 1, and I also have 1 proton. I cannot have any neutrons. It has to be 0. Because if I had neutrons, this mass number would not be just 1, it would be more than 1. Over here, I have a mass number of 4, so protons and neutrons are 4, and I have 2 protons. So I know 2 of these have to be protons. I can just take 4 minus 2 to know that I have 2 neutrons. And so now I can easily say, oh, well, if I have 2 neutrons on this side, I must also have 2 neutrons on this other side. And so I can fill it in right here. Now, if I was going to actually write this in, which I want to make sure you can do, I know that my element symbol will be hydrogen because it has only 1 proton, right? I can also write in my atomic number because there's only 1 option. And my mass number, be careful, it's not 2. It's not my number of neutrons. It's my number of neutrons plus protons. So my mass number here, let me just write this. Mass number for this one needs to be 1 proton plus 2 neutrons, which would be 3. And so this is the atom that we are missing right here, right? That's what you would write into here if there was a blank or a question mark. This would be your answer. And I think we're going to do one more example here that is a little bit more complex looking, but it's actually not more complex. It's not more difficult. There's no other thing that we have to do, but it looks a little bit more challenging. And so it's good for us to take a look at this and say, hey, I'm not afraid of you. You are just the same kind of problem we just did earlier. So this is going to be our 5th example. And now we are actually going to work with plutonium. And so let me draw that in here. So we're gonna have a plutonium atom, and plutonium has an atomic number of 94, and this is a plutonium 239 atom, and so I'm going to write a mass number of 239. And this is actually going to decay, meaning it's not going to react with something, it's actually going to decay into 2 separate atoms here. Okay, and so the first one is that one of the products is going to be a helium atom. So we know that one of the products is a helium atom, but we don't know yet what the other product is, and that's what we want to find out. So I'll draw it this time with a question mark this time. And let's set up our problem the same way as we did before. Again, I'm not going to really bother with my electrons right now. There are no charges here. I'm just not going to worry about that right now. Instead, let's just look at our protons and neutrons. So I don't know these yet, but I can definitely fill in the other ones. So let's do that first. So my protons are easy. That's given to me. It's just 94. That's our atomic number, 94 for plutonium. And for helium, it's 2, right? Now we can actually go ahead and say, oh, well, okay, then it's easy to figure out the number of protons over here. If there are 94 protons on this side of the equation, there must be 94 on this side. So taking away the 2 that are from the helium atom, my other atom must have 92 protons. There's no other option. It must have 92 protons because things don't just disappear, right? So let's look at our neutrons now. Now you might be tempted to say, oh, neutrons, 239, but that's not the case. It's not 239. It is 239 minus 94 because remember that it's the protons and neutrons that give us our mass number. So to find the number of neutrons by themselves, you just take 239 and subtract the number of protons. And the answer that we get here is 145 neutrons in our plutonium atom. And the number of neutrons for our helium atom should be easy to find. We do the same thing. We take 4, which is all the protons and neutrons together, and I subtract my 2 protons to get 2 neutrons. And so here, if I write that in, once again, if we had 145 on this side, neutrons on the reactant side, I must have 145 neutrons on the product side. But 2 of them are coming from my helium, and so my answer must be that this mystery atom has 143 neutrons, because 143 plus 2 is 145, right? And so now we can definitely write in our missing atom. And so the answer here, so this atom has to have 92 protons. And so I want you to look in your periodic table and see if you can figure out what element has 92 protons. So hopefully you went into your periodic table. The answer is uranium. Uranium does. Uranium has an atomic number of 92, and so that means it has 92 protons. And so our element symbol here is a capital U. And I'm going to add in my atomic number of 92. And my mass number needs to be these 2 numbers added up, right? So let me just write my mass number must be 143, which is my number of neutrons, plus 92, which is my number of protons, to give me 235. Let me write that in, 235. And that's my answer. That's my answer. So to complete this equation, I would have to put that into here. Let's just do that so that we have this all figured out. So this would be our answer. That's what our plutonium atom decayed into, a uranium-235 atom. And we're going to stop this video there for now.